from memory. Beyond quantum intelligence, so we use our data, our frameworks, our models to assist clients with insight around the sector. We support a couple of series of clients around the quantum industry globally. And today, I want to talk to you about one particular project we've been doing this year, which was for the NATO Innovation Fund. So, Global Quantum Intelligence, our clients. NATO Innovation Fund is a new €1 billion deep tech venture fund. We worked with them to do a deep technical due diligence on 7 quantum computing players. And this was. Let me talk about the background of how we approached the project. I mean, first of all, I think you've seen this type of chart before. The evolution of conventional digital tech, from vacuum tubes that helped accelerate victory in World War II, through to the transition to the transistor and the evolution of Silicon Valley. And ultimately, this teaches us that this process leads to a dominant design emerging. Complementary metal oxide semiconductor emerged first in the 1970s, and CMOS is still with us today. And what do all of these devices, from the vacuum tubes to the latest super chips, share in common? Of course, they're all Turing machines, and we believe that limits the computational complexity that they can tackle. And of course, quantum computing is our standout candidate to take us through that glass ceiling for the problems we're offering solutions. And so, of course, people are interested. Governments are interested. They want that new Silicon Valley. They want Quantum Valley in their territory. Investors are interested. But what should investors focus on? What should they think about? And a background to this work and our contention is that they should think, if they have the biggest ambitions, about how they can share their prize of that quantum dominant design that will emerge in the future. So how to go about it? So the work we did with the NATO Innovation Fund, we challenged each of the 7 participating companies to tell us how they would build a Shor capable, a machine capable of running Shor's algorithm to factor at RSA 2048 inside one day. And why that challenge? Why did we pick that challenge? Well, of course, cryptanalysis is an important application, geopolitically sensitive. You can understand why NATO would be, but really it was more than that. Because Shor's algorithm, being able to run Shor's algorithm, is a marker for a scale of system that we're pretty confident can tackle a whole series of other very interesting, commercially relevant challenges. And so our contention is that if you create a machine that can scale to that size, you have a good prospect of becoming the dominant design, if you can win in that battleground. And we don't dismiss we don't neglect what might happen with NISC era machines or early FTQC era devices. That's relevant. But if your machine can't go on to win that battle in scaling to be a Shor-capable system, then we think there's a good chance it will ultimately not be the dominant design, and it'll be one of the side exhibits in the Computing History Museum. So obviously the specifics of the work are confidential, and I hope the participants would appreciate that GQI is absolutely all about respecting their confidentiality, a high degree of trust in working with them. But what I do share here is some of the overall factors that emerged as challenges on not one, but multiple roadmaps. So the pink items were challenges on multiple roadmaps, the green disruptive possibilities in multiple roadmaps. And in this presentation, I want to focus on the right, some emerging overall points that we identify as key inflection points that, if they are resolved, could greatly accelerate progress. Scalable modules, efficient fault tolerance schemes, major M&A, a hybrid leap in software, and ultimately the emergence of that dominant design itself. Let me take these. Scalable modules. Now, everyone has modules. And it was great to see Google with its announcement of another great module. And while it's a great achievement, I have to sit there and think, well, its lambda is 2. And it's great that that's moved forward, but we know really the lambda needs to be 10. And it's taken this time to move it forward to 2. the error mod on all of these modules needs to get better. And we can't just review people's roadmaps and just assume that they're smoothly going to get better. They have to have reasons why that error model can improve to a satisfactory point. Also, you have to consider how many qubits are we going to be able to put on a single chip. And you have to think, well, what's the size of these qubits can be? What's a realistic maximum die size I might be able to access? What environmental constraints, cooling capacity, at whatever temperature I have to operate at, optical aperture, laser power, what are those factors that limit really what my module sizes are going to be? Spoiler alert, these are our assessments of where you can get to with first generation qubit type technologies. Spoiler alert, these modules are not big enough, not by far. So you need to either explain how you're going to change that in your roadmap, or you have to face up to the other big challenge, coupling modules together, interconnecting modules together. And there are some honorable mentions of companies that have emphasized progress on this, but for far too many roadmaps, this is neglected. This is deferred. People will say, oh, we will address that at a later roadmap step. But that is a very weak answer. That has to change. If people are going to seriously scale their systems, they have to understand how they're going to do modular interconnect. It's also very useful to, I think, understand that there are two broad different architectures out there at the moment that people are seeking to build. One is really, it's perhaps modules, but it's putting modules, it's extending gate interactions via couplers to ultimately connect those chips edge to edge and create a larger monolithic array of qubits. It's modular, but it's a monolithic array of qubits still. But then there's another strategy, broadly distributed quantum computing strategies, where it's about using measurement to entangle photons across modules. It can be all photonic, but it can also be massive qubits in the modules, but using photons coming off to make those entangling measurements. And this follows in the long academic tradition of measurement-based quantum computing, of cluster-state quantum computing. But it needs us to have new key technologies. Typically we need to worry about a qubit-photon interface, which is going to efficiently get those photons off chip so that I can entangle them. We need a quantum networking unit that's going to make Bell-style measurements to entangle these qubits. It's going to be a fair fight between these two approaches. But we perhaps should realize that there are different trade-offs, and there's some different characteristics about the distributed quantum computing approach. It potentially favors smaller modules that perhaps could be made highly conformant. And if we look forward for a moment to how it interacts with the world of quantum electric codes, these distributed schemes typically naturally offer all-to-all qubit connectivity. And so, wow, it's going to be a fair fight. If distributed quantum computing schemes really take hold, it could potentially be very disruptive in how it accelerates the SEC. Quantum error correction and fault tolerance, of course, the surface code, the OG of our approaches, part of the lore of how we first thought we'd be able to do this. And of course, we now realize that the overheads are eye-wateringly high. And it's not just that scaling of how the encoding rate of my qubit scales. And to get to Shor, I'm going to have to dial up a high distance, perhaps a distance of 23. The encoding rate's very poor, but it's not just that. When I look at how I'm going to do my decoding, typically I'm going to have to assume that I do multi-shot decoding. I'm typically going to assume that I'm going to use D rounds of cycle for each decoding event. That's a big overhead if my D is 23. For lattice surgery, it's a great flexible way of doing my gates. But again, in parallel, I'm going to have to assume I've got D rounds of overhead to do my lattice surgery. And even then I've got magic state factories to lay out to complete the process. So, as we all know, over the last couple of years, this has become a hotbed of activity, coming up with new approaches. And it's partly quantum LDPC codes, of course, which has a broad class of codes, offer almost ideal parameters in terms of the scaling of encoding rates and distance with the number of qubits. But we have to look at, when we look at what a specific company is doing, we have to realize that they're often talking about a very specific code, the gross code, these bicycle codes, and they have specific finite parameters, which may not be quite so ideal. And often on top of this, we don't yet know exactly how we're going to do our gate operation. And we need to realize that it's not just quantum LDPC codes. It's all these other very interesting innovations which are tackling other interesting new techniques to tackle other parts of the problem. Yes, it's bosonic codes to improve the starting point, support better code concatenation. It's fine graining to let me amplify out my distance properties. It's hyperbolic surfaces to give me a more flexible, some new geometries to play with. It's this bouquetization, turning my qubits into a more dynamic approach to how the stabilizers are executed, more flexibility. It is single shot error decoding, where I can construct a code that lets me just run one shot in the code cycle to generate the decoding noises. I can exploit my understanding of the biases in the noise to design my code. There's lots of innovation. And one of the things I would really observe is when you go now into and look at a pitch deck or sit in an investor meeting with one of these businesses, this is the things that are being talked about are not even making their way first into archive papers, never mind into refereed journal publications. So it can feel like the Wild West in terms of how people are feeling that they assemble this together. Now, don't get us wrong. We do not dismiss the possibility that the surface code may be the way that ultimately get this done still. It's our best known approach, our most well-studied, most de-risked approach. But if one of these new approaches can be stood up properly, shown to work, then it could be very disruptive on scaling assumptions in the set. So we're letting the hardware improve. We're letting the software and we're letting the codes improve. It would just be wrong to not also let the software improve. And is there evidence for that? So here I list some of the key original dates for Shor's original seminal discovery of the algorithm, the early optimization period through to about 2017. After that, we had a series of key influential resource estimation papers from Google, from PsiQuantum, other important contributions from Sackley and Alison Bob and Universal Quantum, looking at the effect of different architectures. But if I then look at what's happened over the last 2 years, we have some very interesting stuff again. I'm thinking of the contributions of Regev and Raghavan et al., where we seem to have new approaches to how we may think about deconstructing this problem. And it's part of a theme. Anyway, when we look at HPC, we talk about heterogeneous compute environments, CPUs, different memory resources, and we know that quantum is going to exist in that. But a common theme behind this latest wave of algorithmic innovation, it seems to us that we're often taking what were monolithic quantum algorithms and deconstructing them and finding that gives us some extra options for trade-offs. So what we defined was not to take as our target for implementing this bar of demonstrating you can run Shor, not one of those existing, this is the existing algorithm. We allowed the resource restraints to tick forward by what we felt was roughly a generation. And so we came up with these ones here, numbers of logic, 3 different architectures depending on really how you could manage the connectivity, numbers of logical qubits, logical error rates, and logical cycle times in units. Roughly this needs sort of teraquark type operation. Now, where's the catch for this? What's the difficult point for this in the algorithm? Well, actually, you sit down in this discussion and, well, to get to a particular logical error rate, you get this newfangled code you claim you've got, you dial up the appropriate D and you've got the logical error rate. You've got that module that's, got this, the right error model that you've got. And you can dial up the right number of logical qubits by just modularly adding more modules. It might end up with a very large footprint, but don't worry about that because it's probably the government paying, so it'll be all right. But get to the logical cycle time, and actually that's a bit of a gotcha. Because to run your code, do your stabilizer measurements, your extractions, you're going to have to make some entangling gates for those ancilla qubits. You're going to have to make some measurements, and they've probably got to be a bit realistic in terms of the laws of physics, and you can't get so easily away from what your logical cycle time is going to be. And so that, I find that strange almost. So this is a bit of a struggle point as we went through in these projects. And I find that strange when you look at so many roadmaps we see present, and you'll hear them talk about the qubits, you'll hear them talk now about logical qubits, and perhaps logical error rates are a good one. We still far too often do we not see anything at all about the projected logical cycle times and how that's rationalized over the generations. And I think that's something that needs to change. So the market dynamics that you deliver into, you're building your quantum computer, the market dynamics also matter. It matters not just that you deliver, it depends, have other companies also delivered a similar scale quantum computer? What use cases have been enabled along the way? So we use scenarios to manage this. These are the scenarios we use in GQI's quantum market model. It's our forecasting and projecting model. The green and the pink ones in the middle are the quantum computing ones, important connections to quantum networking across the sector. But this, we think, is key to understanding at the different roadmap stages, and we calibrate those roughly in terms of the number of operations for the quantum computing ones. Is this the kiloquop era that we've just been propelled into at the moment, or through the way to megaquop, gigaquop, and to Shor capable machines come out there in the teraquop region, those different architecture that again. So it matters which of these scenarios you're in terms of what the dynamics, the competitive dynamics would be. And that could be very important in this M&A roll-up we see ultimately happening in the sector. Whether you're playing offense or whether you're playing defense in that stage, can very much depend on which of these scenarios we're in and how you fare in that scenario. So, how should investors put all of this complexity together? So we argue that it's not just and everyone has challenges, okay? So we argue it's not just the scale of the challenge that the individual player faces at their roadmap, an engineering challenge, a minor scientific challenge, a major scientific challenge. It also matters where in the roadmap that is being addressed and de-risked. So at what stage? Is it early on in the kiloquop, or you wait until it's this mid early FTQC megaquop, or right there in the teraquop where you're finally getting Shor relevance? So different investors have different investment hypotheses, philosophies, different focuses for value, different views. But we argue if you're focused on that long-term value and that long-term view of becoming getting a part of the dominant design, we argue that you should prefer the major risks to be taken up front rather than kicked off down the road, leaving your money tied up against some gotcha further off down the line. Now, it's important to realize that this is kind of not really what's typically done. People often focus on the nice device I have today, demonstrating the next milestone, create some progress, maybe some revenue to generate the next funding rates, but maybe leaving that gotcha out there. Now, so again, I can't share the actual assessments of these actual platforms, of course. This is illustrative data to make the point. Each line represents a company. Each dot on the line represents a specific challenge assessed at one of their roadmap stages. And I was saying how the degree we think that challenge is. And this isn't right, but it looks similar to the real chart. And what can you make of it? This is, it's a bit of a mess. No one has a perfect solution. There are no perfect cookie cutter profiles. But we do argue that if you squint at this, compare it to your investment philosophy, that you can make useful conclusions about which of these fits better with your aspiration and how you want to see your money turned up. And I'd emphasize, we think that this point of view is different to how it's been done so many times up to now. So, now, of course, I've talked about the challenge of getting to Shor. You've seen this type of chart so many times before, Q Day, and I'd want to pay tribute to the Mike McKelly-Mosca's work and the Global Risk Institute and the great survey it does around opinions on this. We think, though, you have to take a lot of care in how you interpret that data. One mindset is to go in and say, right, how quickly do I think we'll get there to build what's the most likely date for such a system? So I think we would stick with the normal consensus that it's 2035 plus. But if you're a risk manager in an organization, or a large organization, you think you have to take a different mindset. You have to take the reasonable worst case mindset, which is not about a balance of experts being right. It could be just about one being right, or even two being half right and being pushed together in some accelerated national program to make it happen. So we think the reasonable worst case date may be much sooner. So thank you very much.